start the class. And yesterday we introduced the method of the joint. So we just do some review. In the case, we learned to treat the truss system as a single object, like this part, and which allowed us to calculate all the external force. So you can see only external force at this system. However, if you want to determine the force in each member, like this member, this member, or this member, you need to use the mass of the joint. Like this figure. When using the method of joints, the calculations, we need to break down each joint and the truss. Therefore, we calculate the force equilibrium for each point. Use the summation f x equal to 0 and the summation fy equal to 0. Okay, so we need to break down each joint and the member. Okay, so then at the point D or B or A or C, we can use the summation fx equal to 0 and the summation fy equal to 0 to solve this problem. Then we can get the force. Okay, and if our object of analysis are like this truss system, we will need to spend a lot of time on the calculations because you can see so many members in this truss system. But if we can identify 0 force members in advance, it will help speed up our calculation process. So if we know which one is the force is 0, we can identify this part, then we can help our calculate speed. Okay, so now let me introduce the 0 force members. The truss analysis using the method of joint is greatly simplified if we can first identify these members which support no loading. Like this part, this system. If we know the AF and AB and ED and DC, no force on this this 4 member, we just calculate the B, F, E, C part. We just calculate this 5 member. Okay. If we know this 4, the force is equal to 0. And why do we decide 0 force members? Okay, because these 0 force members are used to increase the stability of the truss during construction and to provide added support if the loading is changed. Okay, so like this figure, this part and this part is are 0 force members. So in a static condition, the truss is just B, C, E, F can be stable. However, in reality, the truss may be affected by other forces, causing the truss forces to become unbalanced. In each cases, these 2 force members, these 4 force members can help restore the balance. Okay, so next let's learn how to identify the 0 force members. It is found by inception of each of the joints. Okay, so like this figure, we can use draw a free body diagram at the point about the point A. So just two force, okay, just two force, but we don't have the support and the other force at the point A. So when we do the summation Fx equals to 0, you can get the result is the FAD equals to 0. Then when we do the summation Fy equals to 0, you also can get the FAF equals to 0. So we call the member A, B, and AF are zero force members. And then we also can draw a free body diagram about the point D. You also can see we have the two force at here, but we don't have the support and the other applied force. So even you do the summation Fy equals to 0, you also can get the FDC equals to 0. And when you do the summation Fx equals to 0, you also can get the FDE equals to 0. So these two members are zero force members. Okay, so just like the B, C, E, F, this truss system is stable and static. So this is the conclusion. If only two non-columnar members form a truss joint to no external load or support reactions is applied to the joint, the two members must be zero force members. So the key point is no external load and no support reactions. So you can see this part at the point A, no these two, and this at the point D also. Okay, so in this case, we can focus on draw a free body diagram about the point D. Then you can see we have a three force at point D. But when you do the summation Fx equals to 0, if we put the axis at here, you can see the FDA is equal to 0 because no other support, no other applied force. And then when we do the summation Fy equals to 0, axis also, just these two, okay, this is equal to this. So the DA is the zero force member. When we draw a free body diagram about the point C or joint C, we also have the three force at the joint C. And when we do the summation Fx equals to 0, okay, then you can find, because no support, no other force at here, so the FCA is equal to 0, and the FCD equal to FCD when you do the summation Fy equals to 0. So the FCA also is the zero force member. So just use this truss system, we can get a stable static condition. So in general, if three members form a truss joint for which two of the members are collinear, the third member is a zero force member, provided no external force or support reaction is applied to the joint. Okay, so just like this. So if we have this triangular truss here, these two, okay, if this point, this joint and this joint, no support or no applied force or external force, then in general, these two is the zero force members. Okay, so you just try to this example. Using the method of joints, determine all the zero force members of the pin above the truss shown in this figure. Assume all joints are pin connect, so every member use the pin connect. So every part have the just the parallel direction force, and we have the hinge support at here. So we have reactions this direction and this direction. And we also have the roller support at here, so we also get the perpendicular reaction at here. Okay, and then we also have the two force. So we can do the first on the joint G. Okay, on the joint G. Because we need to find the zero force member. So like this part, G and D is the same situation. So the FGC seems equal to 0. Because when you do the summation Fy equals to 0, we can very easy to find the FGC is equal to 0. And as the same conjugate at the joint D also can get this result. So when we do the summation F X equals to 0, we can find the FEF that is equals the force is equal to 0. Then we can focus on the joint F. So at the joint F we have the force F dF for FDF is equal to 0, we know. So if you do the summation Fy equal to 0, I think the FC also equal to 0. So you can see, the answer like this. Okay. And if you focus on the joint B, then you can try to analyze the calculate the summation Fx equals to 0. Then you will know the FBH just equal to 2 kilonewton. Okay, like this. So just find like this this situation, and you can find so many zero. Easy to find the zero force member. Okay, and the method of the joint can sometimes require lengthy calculations. So if we only want to determine the force in the specific members, we can use the method of sections. Okay, so you use the like this system. If you use the method of joint, you need to calculate every joint and every member force and get the answer. But if you want to know, maybe you want to know the BC, HC, and HG, just cut this section. Just cut this section, and we can use the method of the sections to solve this problem. Okay, so let's begin by introducing the method of the sections. If the truss is in equilibrium, the meaning is any segment of the truss is also in equilibrium. To find forces within the members and in generally a section is used to cut each member into two parts and expose each internal force as external force to a free body diagram. Okay, so like this figure, when we cut this member, we can get the internal force. Okay, we can get the internal force. when the member get the compressive force also, when we cut this, we can get the internal force here. Okay, so the method of section also use the cut of section the members of an entire truss. Only three independent equilibrium equations are summation fx equals to 0, summation fy equals to 0, and the summation mo equals to 0. Okay, just select a section no more than the three members in which the force are unknown. Okay, so like this truss system, when we do the method of sections, we just choose the three. Okay, just like this section A, paste the cut pasting the three members. Then we can draw the left part free body diagram like this. Then we also can draw the free body, right part free body diagram, okay, like this. So this is a note. The force in the member is along this axis. So like this part, when we cut this, the force just along its axis, And the member forces are equal and the opposite. Those acting on the other part is according to the Newton's law. Okay, so the meaning is, okay, this is equal to this, and this is equal to this, and this is equal to this. And we have two ways to determine the current sense of an unknown member force. First one by the inspection, and the second is always assume that the unknown member forces at the cut section are tensile forces. For example, occurring on the member. By doing this, the numerical solution of the equilibrium equations will yield. Okay. So the positive scalar for member in tension, and the negative scalars for members is a compression. Okay, so we can do this example. Determine the force in the members GE, GC, and BC of the truss shown in this figure. Indicate whether the members are in tension or compression. So we want to determine the member GE, GC, and BC. So we just use the X section to cut. Then we can draw a free body diagram first. Sometimes we can use the previous method, or just you set the truss system is the one object. Then we can draw the free body diagram only external force. Okay, so we have the one pin support at here, and we have the roller support at here. So we have these three reactions. And we have the two forces here and here. So this is a previous method. We can draw the free body diagram in one object, and we can use the summation fx. Then we can very easy to calculate the ax. So the ax like this. Then we can put the moment point at here. Then do the summation of ma equals to 0. So we use this force and this force and this force times the moment arm. Then we can get the summary. These three forces let this point get the moment is equal to 0, so we can get the dy force result. And don't forget, we wrote according to the right hand rule, so this force and this force, okay, let the point A get the negative moment, and this force let the point A get the positive moment. Okay, then the dy is equal to 900 Newton. Then we also can do the summation Fy equal to 0. Then we can very easy to calculate the Ay is equal to 300 Newton. Okay, so this is the previous result. We can get the action force first. Then, because we cut the face at the section A, so we want to know the FGE, FGC, and the FBC value. So we can set the moment point at the point G is equal to 0. So we don't care this force and this force. We just use this force, and this force, these three forces. Let the point G get the moment, and combine these three force moment is equal to 0. So the calculate like this part, then we can get the FBC is equal to 800 Newton. And we also can set the moment point at the point C. Okay, and the point C is the FGC direction, and the FBC direction. Extend the line, then connect together at the point C. So we can set the moment point at here. Then we just use this force and these two forces, and then calculate the moment at the point C. So we can do the summation. NC is equal to 0, and use this equation to get the FGE answer is equal to 800 Newton. Then if we know the FGE and the FBC, I think we can do the summation Fy equal to 0. Then we very easy to calculate the FGC answer like this. We also can do the summation Fx equal to 0. I think we can also get the same answer. The FGC is equal to 500 Newton. The next example, determine the force in the member CF of the truss shown in this figure. Indicate whether the member is in tension or compression. Assume each member is pin connected. Okay, so we want to know the CF. Okay, we want to know the CF. So we cut. Okay, we can cut the section A. Okay, passing the three members. We don't cut it here. Yeah, because when we cut this section, we pass in the four member. Is we can do the method of the section. So we just cut like this. Okay. But when we before we calculate the every member force, we can do the free body diagram about the entire system, entire member. So we have the one support pin here, and we have the other support here, and critically we have this direction reaction, but you can see we only these two force under this plane. So like the beam, like a beam at here. So we don't calculate this reaction, because this reaction is equal to 0. When we do the summation Fy equal to Fx equal to 0, you can get this answer. And we have these two force like here, so we can set the moment point at the point A, then we can calculate this reaction. When we set the moment point at the point E, then we can calculate this reaction. So like this part, and so we can get this answer. And we cut the section A, so we can choose draw the left part or right part. But I think right part is easy because just a little members. So we draw the right part. Then we need to calculate these three forces. So okay, so because we want to know the CF, right? Okay, we want to know the CF. So when so we can use the FG direction and the FCT direction, then extend the direction line, connect in one point. When we set the moment point and at this connect point, we don't care the FG and the FC. Just use these two forces and FCF force, calculate the moment at the point O. So the summation MO is equal to 0. Then use this force and this force and this force times the moment on. Then summary, these two moment is equal to 0. Then we can get FCF is equal to this answer. Okay, next example. Determine the force in member EB of the roof truss, shown in this figure. Indicate whether the member is in tension or compression. So we also just draw a free body diagram like this, and when we want to determine the force in member EB, you can choose the B section, and when you choose the X section, you will get the 4 unknown. Okay, so I think it's very difficult to calculate, but if you just only cut the section B, you also it's very difficult to get the answer. So we just cut this part. Okay, cut this part. Then we set the moment point at point B first. Okay, we set the moment point at point B first. Then because this force are passing this point, so we just use this force and this force and this force and this force FED to calculate the moment at the point B. So summation MV equal to 0, like this equation, then we can get the FED answer like this part. Okay, when we have the FED, we can go back to section B. Then we can draw the point E, section B, free body diagram. Then, so we have the this force and FDE. We use this calculate, and we have the 2 unknown. Then we just use the summation Fx equal to 0 and the summation Fy equal to 0. Then calculate this. Okay, so when we do the summation Fx equal to 0, okay, just use this and this. So I think these two is same. Okay, it's same. And when we do the summation Fy equal to 0, just use this force and this force. So the FEB is equal to 2000 Newton. let's move on to introduce the space trusses. This concept is simply a transformation from 2-dimension to 3-dimension. A space truss consists of members joined together at layer ends to form a 3-dimension structure. This space truss is a heterohedral formed by connecting 6 members. In 2D, we call the triangular truss only a 3-member. Okay, so in 2D, maybe just like this part. Okay. Then we call this is the triangular truss. But in 3D, we call the space trusses. We have the 6 member. Additional member would be a redundant is supporting a force P. Okay, so we explain the assumptions for design. Members of a space truss is treated as 2 force members, provided the external loading is applied to the joints, and the joints consist of ball and socket connection. When weight of the member is considered, apply it as a vertical force, half of its magnitude applied at each end of the member. Okay, so this is the example. Determine the force acting in the members of the space truss shown in this figure indicate whether the members are in tension or compression. Okay, so in a 3-dimension problem, we can use the Cartesian vector form, then we can easy to calculate. So at the joint A, we draw the free body diagram first. So we have the 1 force here, and we have these 3 member force. Okay, so we have a 4 force. Then we also can use the Cartesian vector form. So the P parallel y direction, y-axis, parallel y-axis, but it's negative, okay, because the positive is here, so this part is negative. So the P is equal to minus 4J. Okay, the J means the parallel y-axis, and the FAB, okay, also parallel the y-axis, but on the positive part. So we use the FAB is equal to FABJ, and the FAC. Okay, then we FAC just parallel the z-axis, and the direction is the negative. So we use the negative XAC K. The K means the parallel z-axis. And the FAE, we use the force value and times the unit vector. So I think the unit vector just use the reaction, the vector divided by the distance. So this vector from A to E, okay, from A to E. So the x is equal to 2, y is equal to minus 2, and the d is equal to minus 2. Then we can use this vector to calculate the unit vector. Then we can get the FE like this, represented like this. So when we do the summation F, we just summary these four forces combined together is equal to 0. So we can combine the I part and the J part and the K part. Then when we do the summation Fx equal to 0, the mean is the I part is equal to 0. So we can see the I part at here, just use this equal to 0. Then we can get the FAB answer. And then when we do the summation Fy equal to 0, it's same concept, just combine the J part, J part, and this J part, and equal to 0. So we can use this result, put inside, then get the FAB answer. And we also can do the summation Fz equals to 0. The mean is the summary of K part is equal to 0. So we can find this equation. Then the equation, let me know. The AC, because FAB is equal to 0, so FAC also equal to FAE also equal to 0. Then we can use this equation and find that FAB is equal to 4 kilonewton. Okay, so now we just finish this member force and this member force and this member force. We also have the joint E. We have this force, and this force. Okay, so we just draw the free body diagram at the point B. Okay, so we have this. Okay, and we have 1, 2, 3, 4, 5. We have 5 force at the joint E, and we know this force, and we also know the FAB answer because when we calculate the joint A, we have the FAB answer. So now we have 3 unknown at here. Then we just we don't use the Cartesian vector form. We just do the summation Fx equal to 0. Then we can very easy to find the answer. So FBE times this part is equal to 0. Then we do the summation Fy equal to 0. Then we can get this equation. Then FCB we can have the answer. Okay. Then we do the summation Fz is equal to 0. And we have these two answers, right? So put these two answers in this equation, then we can get the FBD answer. Okay, so this is the answer of the point joint B. And we also have the three member need to determine. But don't forget these 3 parts on the same coplanar. So this 3 part is equal to 0. Okay, is equal to 0. Okay, so let's move on to introduce the frames and machines. It is a composite of pin connected multi-force members. Frames are stationary to support loads. Machines are moved apart. So apply the equation of equilibrium to each member to determine the unknown forces. Therefore, the upcoming example will include more and more components. So, okay, like this previous example, we just only the support and truss member. But now we will have so many objects combined together. Okay, so like this part, okay, we have the two support and this member and this member, then use the pin connect together. Okay, so we call this the frame. Okay, so we do this example for a frame showing this figure. Draw the free body diagram of the. Okay, we need to draw the three part. First part is each member. So we need to draw each member. Okay, and the pin. Second is the pin at the B and the A. The pin at B and the A, and the two members are connected together. So I think the C is equal to is very easy because just internal force free body diagram. So just use the previous method. So we can very easy to draw this because we have the two pin support in here. So we have two direction reactions. Two direction reactions. So like this part. Okay, we have two reaction, and we have the one moment here, one force at here. Okay, one moment here, one more force at here, and because the B let the two member connect together. So I think this part just internal force. If you draw the entire entire system, we don't care the internal force because we just only external force. Okay. So I think the C is very easy. Okay, that is like this part. And okay, when we draw the each member free body diagram, just use like this external force, and when we cut this part, then we can get the internal force. Because this part is the pin, okay, so the internal force also have the two direction force. Okay, so if this member have the internal force, so I think this part just like this. So we have this direction internal force. In this object, we also have this direction internal force. So use the same concept, you can draw these two member free body diagram. And at the point B, okay, just the one pin. And at the pin, because we have the two member, one at here and one at here, so we need to draw the four force at here, because one member we have two direction force, and at the point A support pin support A, we have the reaction at the AY and the AX, but the pin also have the this part and this part. So this part and this part have also have the two direction reactions. So and the value just the AY divided by 2. Okay, each part have the force. Okay, so I think just very easy to draw a free body diagram. Okay, so this is another example. A constant tension in the conveyor bolt is maintained by using the device shown in this figure. Draw the free body diagram of the frame and the cylinder. Let the bolt surrounds the suspended rod has a weight of W. Okay, so like this figure, we have the this is the pin hinge or pin support, and we have the one pin like this part, and we have used the cylinder, or we call it pulley. Then this pulley connected to one swing. So this we have a tension force at this swing, and these two parts the tensile force is same, and we also have the one block, and this block have a weight. Okay, so we need to draw a free body diagram in two objects. Okay, two objects. One is the beam and one is the pulley. So in the beam, we have the one support. Okay, so this is the pin support. So we have the two direction reactions, and we also use the pin connect the pulley and the beam. Okay, so this is the pin. So we also have the two direction force, and on the this side we have the weight. So we draw like this. And about the pulley, okay, we use the swing connect this pulley. So we have these two tensile force, and at the pulley center we have the pin connect pulley and beam. So we have the internal force. Okay, it's just like this force and this force and this force and this force. Okay, so we just 10-minute break and go back to the colors.